Electrons as fundamental particles. Electrons are considered fundamental particles, which means they are not composed of smaller subparticles. They are elementary particles with specific properties that play a fundamental role in the structure of matter. These properties include mass, electric charge, and magnetic dipole moment. Classical electron orbits. In classical physics, electrons orbiting the nucleus of an atom might be envisioned as similar to planets orbiting stars in a solar system. This classical picture, however, encounters a significant problem when we consider the behavior of electrons in atomic systems. Radiating energy, and orbital collapse. According to classical electromagnetism, an accelerating charged particle, such as an electron in orbit, should emit electromagnetic radiation. This emission of energy implies that the electron would gradually lose energy, spiral inward, and ultimately collapse into the nucleus. This classical model raises questions about the stability of atomic structures and contradicts observations of stable atoms. Development of quantum mechanics. To address the limitations of classical physics in describing atomic behavior, the theory of quantum mechanics was developed. Quantum mechanics provides a more accurate framework for understanding the behavior of electrons in atoms. It introduces the concept of discrete energy levels and the wave-like nature of matter. Quantum states and energy levels. In quantum mechanics, matter, including electrons, is described by wave functions. These wave functions represent the probability distribution of an electron's position within an atom. Electrons are constrained to exist only in certain discrete energy states or levels within an atom. The energy levels are characterized by quantum numbers and are related to other properties like angular momentum. Quantum jumps and photon emission. Electrons can change their energy states by absorbing or emitting energy in the form of discrete packets called photons of light. These transitions are quantized, and electrons can make quantum jumps between energy levels. This behavior is what gives rise to the discrete lines in an atom's emission or absorption spectrum, preventing the collapse of electrons. One might wonder why electrons don't continuously radiate energy and collapse to the lowest energy state within the nucleus. This is explained by the fact that there is a minimum allowed energy state. Below this minimum energy state, there are no more energy levels available. This minimum energy state is centered around the nucleus, and it has zero angular momentum. Instead of thinking of this as an orbit, it's more accurate to visualize the electron's position as a cloud of probabilities. Heisenberg's uncertainty principle further contributes to the diffuse nature of this cloud. Spin and the Pauli Exclusion Principle. In the framework of quantum mechanics, electrons exhibit an additional intrinsic property known as spin. Although it shares similarities with angular momentum, it is not tied to physical rotation. Instead, an electron's spin influences its behavior within an atom. The Pauli Exclusion Principle, a fundamental principle of quantum mechanics, dictates that electrons with identical spin values, spin half for electrons, cannot simultaneously occupy the same quantum state. This principle is of paramount importance in elucidating the structure of atoms, giving rise to the concept of electron orbitals or electron shells. It fundamentally shapes the organization and distribution of electrons around the atomic nucleus, forming the basis for our understanding of atomic properties and chemical behavior. Atomic structure and stability. The atomic structure can be conceptualized as a container that houses electrons. The positively charged nucleus creates a potential well that effectively traps free electrons. To achieve stability, these free electrons must shed their excess energy by emitting photons until all the lower atomic energy states are occupied. Once this energy loss process is complete, the electrons can no longer shed any more energy, leading to the establishment of a stable atom. This well-structured interplay of electrons and energy states is fundamental to our understanding of atomic stability and the behavior of matter. Extreme gravity and neutron stars. In the cosmos, under the influence of extreme gravitational forces, atoms are subjected to immense pressure. This pressure can cause the compression of atomic nuclei and electrons, reaching a critical point where electrons interact with protons. This process leads to the formation of neutron stars, astoundingly dense celestial objects primarily composed of neutrons. Neutron stars resist further gravitational collapse due to the Pauli Exclusion Principle, giving rise to a phenomenon known as Fermi pressure. Black holes and the unknown. As we delve into the enigmatic realm of black holes, the well-established laws of physics begin to unravel. When gravitational forces become overwhelming, surpassing the resistance of Fermi pressure, objects can collapse, forming black holes. Inside these mysterious entities, the laws of physics become highly speculative and theoretical. Classical physics and even many aspects of quantum mechanics may fail to accurately describe the conditions within a black hole. Theoretical physics, particularly the exploration of singularities and the nature of spacetime within black holes, remains a subject of intense research and debate, signifying the profound mysteries that continue to challenge our understanding of the universe. In conclusion, captures the essence of the complexity and interconnectedness of the fundamental principles governing the behavior of matter, from the microscopic world of quantum mechanics to the vast scales of the cosmos. Despite the significant progress humanity has made in unraveling these mysteries, the journey of scientific exploration continues to reveal new questions and challenges, reminding us of the boundless depths of the universe's secrets. The pursuit of knowledge in these fields remains one of the most exciting and intellectually stimulating endeavors, propelling us towards a deeper understanding of the fundamental fabric of our reality. Thank you for watching another episode of Odyssey. While you are still here, don't forget to like and subscribe.